Hey guys, welcome back. So in our previous video, we have seen a simple introduction to the digital systems and where it is used. Now in this video, we will start with the exact core component of the course. Now, in order to just understand a digital system, we need to think about a lot of decision making, and decision making doesn't come simple. So we need to find out a lot of logical items here. So when we are trying to find out what is a logical system and how do I make decisions based on the logical system, finally I end up in a situation where I need to think about numbers. So what are these numbers and what do we mean by number system on the whole? So let's get started now from this number system. We have a simple question here again. So what is a number system? Number systems is a way of expressing numbers and its values. Like I can say a number like 75. So it's pretty simple. 75 is a decimal number, but how do I get that value 75? So it's like when we speak about decimal numbers, then we have to think about the base of that number and how this base is trying to represent my number so that finally I get a value of 75 with me. So progressing further, it's again a mathematical notation for representing numbers in a given set. And that set could have digits or other symbols which is in a consistent manner. It keeps on repeating again and again. And also the same sequence of symbols may represent different numbers in different number system. So when we are speaking about number system, I can say that we have base 4 number systems like decimal or binary number system or octal number system or even hexadecimal number system. So the number 8 in an hexadecimal number system can vary from other number systems. The number 1, which represents some quantity in a binary number system, can represent another quantity in a decimal number system. So that's the idea here. The same sequence of symbols may represent different numbers in different number systems. For example, like what I said, we have binary, octal, hexadecimal, decimal, and we do have some kind of examples here. The number 1101 that represents your binary number system. 127 can be represented either in decimal or it could be an octal number system that qualifies both. 12EF qualifies a hexadecimal number system. This again can be given as an hexadecimal number system or it could be even a decimal number system. So we will see that later in our course as we progress further. Now, how do we represent numbers? For example, let's say I have a number 756 and of course I'll take an example of a decimal number. So I assume this is a decimal number. How this number is represented or how do we calculate the value of this number? So this number being in a decimal base, so the value is calculated right from the first bit, which we call it as the least significant bit. Then we have the next bit and the last bit of this number, we call it as most significant bit. Okay, so the first bit is least significant bit from my right hand side and the last bit is most significant bit. So that's why we start calculating the number. So you take the least significant bit, multiply that with the base of that number system, raised to the power 0. Then you add that with the next bit, multiply with the same base, but this time raised to the power 1, that is 0 plus 1. And again, the third bit, that is the last bit, according to this number example, which is 7 into 10, that is the base. And again, multiplied with the power raised to 2 here. So the power keeps on increasing by 1 at every step. That's how we try to calculate the total value of this number. So 7 cross 10 square, that gives me 700, plus 5 into 10 power 1, that gives me 50, plus 6 into 10 power 0, anything raised to the power 0, that gives you a value of 1. So 6 into 10 power 0, that is 6 into 1, that gives us 6. And finally, that's how we landed with the number 756. Maybe we can take another example here. So I have a number 153.89. So the last number was a whole number and this is a fractional number what we have here. So how do we calculate the value of a fractional number in a decimal number system? So this 3 is my least significant bit in the matrix part and this 1 is the most significant bit and this is the fractional part what I have. Yeah. So let's start from the least significant bit first. So I have the least significant bit here. So that is 3 into 10 power 0. Then I have the next bit, that is 5 into 10 power 1. Then I have the last, that is the most significant, that is 1 into 10 power 2. So this will give me the integer part or the Mantis part. Then speaking about the fractional part. So we start from the first bit, what we have here, 8 into, this time 10 is raised to the power minus 1 because it's a fractional part. So minus 1 is nothing else but it's like 1 by 10, and minus 2, 10 power minus 2 is nothing else but like 1 by 10 square, and it keeps on going as we progress further. So 8 into 10 power minus 1, that's the first quantity what we have, plus 9 into 10 power minus 2, that's the second quantity what we have. Now gathering all the data what we have here, we have 100, that is the first bit here. Then 5 into 10 power 1, that gives me 50. Then 3 into 10 power 0, that gives me 3, plus 8 into 10 power minus 1, that is like 8 into 1 by 10. So that gives me 0.8, that's what we have here. The 9 into 10 power minus 2, that gives me 0.09. So when you add up all these numbers, you will end up at the answer 153.89. So when we try to represent these numbers, of course, we do have a common representation, and we do have certain notations. So we will see that now. So any number can be represented in this form of like a to the index 5, 4, 3, 2. So I can have a common notation like a 0, and it keeps on going till an minus 1 dot a minus 1, and it keeps on going to am or minus n. So that's what we can understand here. So any number in a decimal system will be in this form. So 10 raised to the power into the coefficient of that number, the index value, and it keeps on increasing. So here a represents the each and every bit of that number, which we technically call it as the coefficient, and the value 10 here represents the base of that number system. Since we are having an example of decimal number system, the base is 10, but depending on the number system, it might change. If it is octal, we will have a base value of 8. If it is binary, then we have a base value of 2. If it is hexa, then we will have a base value of 16, and so on. Okay, it depends on the base value. So that's what I said. A represents the coefficient, 10 is the base, and the other name for this base is radix. So some of the authors they mention the base as radix in their books. So please don't get confused. Both base and radix can be used, and they mean the same. And the powers are based on the indices of the bits, the position of the bits. So let's take a pause here, and please try to represent this number 512.3. Again, I have a base representation here, which means it's of base 5. I want you to represent that in the decimal value. So what we can do is, I can start with my least significant bit. So I have 2, and since my base here is 5, so I start with 2 into 5 power 0. Then I will take this next digit, that is 1 into 5 power 1. Then I take the last one, which is the most significant bit what I have here. So that is 5 into 5 power 2. So that gives me 5 cross 25. Then I have plus 1 into 5. Then I have 2 into 5 power 0, that is 1. So 5 cross 25, that gives me 125, and 1 cross 5, that gives me 5, and 2 cross 1, that gives me 2. So finally I'll be having a value 132. That's the final answer. Okay. And the next example what we have here, I have not mentioned the base, but it's understood since we have zeros and ones, we can assume that it's a base 2. So when you want to represent this one into a decimal format, since the base is of 2, we start with the least significant bit, that is 0. So maybe I can write it down here. So 0 into 2 power 0, plus I'll take the first one, 1 into 2 power 1, plus the next bit is again 0. So 0 into 2 power 2, and you can keep on going till you reach the Mantis part. So moving further, we have 4 basic number systems. What we are going to deal with is in this course. So one is decimal, which is having a base value of 10. Next one is binary, which has got a base value of 2. And the third one is octal, and the final one is hexadecimal, as we have mentioned before in earlier stages. So a small activity for you people. Please take 2 minutes time and try to identify under what base these numbers could be accommodated. So if I come back, if I start with the first number 5980, okay. So this number cannot be of base or binary number because it's not zeros and ones. So it's more than that. It could be a decimal number, yeah, and it could be an hexadecimal number, yeah, that's fine. But it cannot be an octal number because the value is crossing the limit 7. So when we speak about decimal numbers, I have a set of numbers from 0 to 9. When we speak about binary numbers, we have 0 and 1 in that set. When we speak about octal numbers, we have totally 8 numbers, but it starts with 0 and it ends at 7. Whereas when we speak about hexadecimal numbers, it starts with 0 and it ends at 15. But in order to make this representation easier for us, so they have designed in such a way that it starts with 0, goes till 9. But the next number from 9, which is 10 exactly, 11, 12, 13, 14, and the final number is 15. So these 2-digit numbers are represented with the help of alphabets or characters. So 10 is represented as A, 11 is represented as B, 12 is C, 13 is D, 14 is E, and the final number 15 is F. So your hexadecimal consists of 0 to 9, then followed by A, B, C, D, E, and F. So that's how, since this number doesn't satisfy this criteria, it cannot be an octal number as well as it cannot be a binary number. So it has to be either a decimal or a hexadecimal number. The same case for the second example here, it could be a binary number, it's allowed. It cannot be it could be a decimal number, it's allowed. It cannot be a binary, no. But I guess it can be an octal here, and also it can be a hexadecimal. The third example, again, it could be a decimal, it could be an octal, it could be an hexa, and the final one, the same thing. Okay, so we can have another number, let's say, okay, 10111. So this number could be a decimal number, yeah, it's possible. This number could be an octal number, yeah, that's possible. It could be an hexadecimal number, yeah, that's possible. And it could be even a binary number. So it satisfies all criteria. So in order to make it clear, or the numbers what we use in a digital system, it's always better to have brackets over these numbers and mention the base below them so that it's the right representation. Moving further, let's do some conversions. So let's say I have a binary number with me, and I have 1101. I want to convert this number into a decimal number. So what is the operation we follow here? So let's start from the first step. So I want to convert something to a decimal number. So what I do, I take the number as such, I take the least significant bit, multiply them with the source base value raised to the power 0. Then I take the next bit, multiply with the base value raised to the power 1. Next bit, multiply with the base value raised to the power 2. And the last bit raised to the power 3. So this gives me 1. This is again 0. This gives me 4. And this gives me 8. So on the whole, you'll be having 13. So which is a decimal number. So this is the process what we follow to convert a binary number to a decimal number. So I repeat it. So first we try to take the number's least significant bit. We start from there. We go till the most significant bit. And at each step, we multiply that with the base of the source number, which is binary, raised to the power 0, and it keeps on increasing. So the operation what we follow here is multiplication. And also the base what we follow here belongs to the source number, or not the destination. The destination here is decimal. So finally we get a decimal number. So let's do the opposite way. You want to convert a decimal number to a binary now. So what we do, let's take the same example 13. I just want to convert that into some number which is binary in nature. So this time the operation varies. So let's get started. So I have that number. I'm going to do division operation, but this time the base what I'm going to use is not of the source, but it's of the destination. So the destination number is binary number, so I'll be using that base. I just divide this number with my base value 2. That gives me 6, which is 12, and I have a remainder 1. Again, I'm going to divide it further. I have 3 with a remainder 0. Then I divide it further. I have 1 with a remainder 1. So I cannot divide it further, so I stop here. So I will start from this point. I will go to the starting point. The numbers on the way gives me the final binary number. So I start with the first value, that is 1. Excuse me. Yeah. So the first value is 1. The second value is another 1, which is here. The third value is 0, and the final value is 1. So this gives me the binary version of the decimal number 13. So just a revision here. So if you want to convert a decimal number to a binary number, the operation what we follow here is division, or like LCM method, which we commonly call it. And the base what we used here to do this operation is of the destination numbers base. So that's the idea here. Now let's try to work with an octal number. Let's say I have a octal number, okay, 162, and I want to convert this number, octal number, okay, just I'll keep the base 8. I want to convert that number to a decimal number. So again, any number, if it has to be converted to a decimal number, we follow the same technique. So we do multiplication here. So I take 162, I take 2 into the source base value is 8, so 8 power 0. Then I take 6 into 8 power 1. Then I take 1 into 8 power 2. So here I have 2 cross 1, that is 2. 6 into 8, that gives me 48. And I have 8 square, that is 64. So here I have 2 plus 8, that's 20. 10 plus 4, 14. I carry 1 further, so 5 plus 6, 11. So this is a decimal number. So it's pretty simple. We follow the same technique. We take the base number, that is, the source number, that is 162, with a base of 8. You convert that into decimal number. Follow the same strategy of multiplication. And this time the base value is the source base, that is 8. So if you want to convert this back, or you want to do the opposite operation, which is like you want to convert a decimal number to an octal number, it's pretty cool here. So I do the division operation here. Let's take, you want to convert the decimal number 114. So you take 114, divide that with the destination base, that is 8. So if you divide this by 8, it goes like 1 times, then we have 34. So which is 4 times, that is 32. That gives me a remainder of 2. So what I do, I divide it again by 8. So I'll divide it once. I have a remainder of 6. So you start from the scratch point here, go till the top. So you read it one by one, 1, 6, 2. So that's the resultant value. And it's pretty the same number what we have here. So let's try to understand it further. Let me convert another number. Let's say I have a binary number 110.10. This time we'll take a fractional number. Now we want to convert this into a decimal equivalent. We know that this is a binary number. We want to convert that into a decimal equivalent. So we can divide this into 2 portions if you want, or we can do it directly here. So let me take this portion first. I'm going to deal with the max part. So I take 0 into 2 power 0, that is the first value. Then I take 1 into 2 power 1. Then finally the third one into 2 power 2. So this gives me 0, this gives me 2, and this gives me 4. So on the whole we have 6. Now dealing with the rest of the fractional part, you take the first number, multiply that with 2 power minus 1 this time. You take the second number, you multiply that with 2 power minus 2, and you keep on going with the rest of the numbers what we have. So since in this example we have only 2 fractional bits, we stop here. So this gives me 1 by 2, that is 0.5. This gives me 0. So this total value is 0.5. I'm going to add these two, so that gives me a final answer 6.5. Okay, so 6.5 is the final value, which is the decimal number here. So moving further, what we can do is, let me convert this back for you. You want to convert a decimal number to a binary number, but this time the decimal number is a fractional number. So how do we do it? We'll take the same operation. We take the mantis apart first. We try to divide that by the base value 2. So you have 3 times, no remainder. You have 1 time, you have 1 remainder. So let's take this separately and keep it above. So I have 110 on my hand. Now what about the fractional part? How do I calculate it? So you take the fractional part as it is, multiply that with the base value. So that will give you an answer 1.0. Now again you take this fractional part, multiply that with the base value, and you have to stop till you get a value 0. So here I have got a value 0. So it's like I'll be carrying these values, the mantis part of this operation. So that gives me 10. So initially I had 110 with me. Now I have 10 with me. So the final answer is 110.10. So that's how we do conversion between decimal and binary in terms of fractional numbers. In terms of normal, whole numbers, we have already seen that in the previous slide. So let's take a shortcut now. So you want to convert an octal number to a binary. So what we do in this case, so one option is that I can convert an octal number to a decimal number, which is already I know. We have seen that in the previous examples. Now after converting this, you convert the decimal number into binary. So this is a straightforward way of doing it. There's another way of doing it in a shortcut way. We can directly convert an octal number into a binary number with the help of the digits representation. I hope you people can do the first option by yourself. Let's deal with the second option. Let's say we have an octal number 135 and you want to convert this into a binary. So any octal number's base is 8. So if you want to represent 8 in terms of powers of 2, how do we do it? So it's 2 power 3. So this gives us a sparse idea about the number of bits that can be used to represent an octal number. So that is 3. So what we can do is we can take each and every bit of this octal number, represent that into a binary number with a limitation of 3 bits. So let's take the first one, 5. 5 can be represented in binary with respect to 3 bits in 101. 3 can be represented as 0, 1, 1. 1 can be represented as 0, 0, 1. So this whole value gives me the total binary value of this octal number 135. And the reverse is also possible. So let's say you have a number 1011101. You want to convert this into an octal number in a shortcut method. The regular method is you convert this binary number to a decimal first, then you convert that into an octal. That is possible. But this time let's try to understand the shortcut method. So if you want to do it in a shortcut method, take the octal number as it is. From the right hand side, from your least significant bit, divide the number into segments. Each and every segment should have 3 bits. So from my right hand side, I am taking 3 bits. And next I am taking 3 bits. The last one I am left with only 1 bit. So I just add some 2 zeros. Okay. So this number in decimal format is 5 for me. This number in decimal format is 3. And this number in decimal format is 1. So this gives you the final answer of your octal number. Hope it is understood. The same thing can be done with the 4 bits where you want to convert an hexadecimal number into binary. That's also possible. Or if you want to convert a binary number back to a hexadecimal number, you can follow a similar strategy where you divide that number into bits of 4s and try to identify the hexa value of them so that you will get the answer. So that's it for today's video. Just a short rollback. We started with the number system. We tried to understand how they are represented in decimal and other formats. Then we took some examples and we tried to find out the value of those examples. Then we finally landed in the position where we tried to convert these numbers from one decimal or one format into another format. We have dealt with four different number systems here. One is your binary number system, the decimal number system, the octal, and the hexadecimal number system. Hope it is clear for you. Thank you for your time. We'll meet in your next video.